took a look at your flow chart. It's pretty good actually. I think you got most of the conditions. Basically, what I can see is this is the main activation, lah, right? You are
Yeah.
going for key 1, key 2, key 3, and you've got all your escape sequences in case. And if it's a match, then you're enabling this state transition, correct? The
Yeah.
door one. And this is the one where you're actually looking at updating the keys, the password, right?
Yeah.
You only update the password at this point, otherwise you
Yes.
escape to this state, right?
Yeah.
Okay. So this kind of documentation is kind of nice if you can just kind of mention it like briefly lah
Okay.
in a in also the text form. But this one I like it lah because very easy to understand and straightforward lah. Now the only thing here that I don't see is where
Yeah.
are you storing your password for comparison? Where is the part where the start password is being compared lah, right? Because here, like as you said, these are the modes. You see, you're moving from one mode to another, huh?
Yeah.
But
Yeah.
here is where you're actually doing the comparison, right?
Yeah.
But you have not specified how you're generating this signal, lah. This signal, you know.
Oh, okay.
Right. So in order to do that, you
Mhm.
sketch it out lah. So the first question I want to ask you is, do you understand how to transform this, and this into circuit diagram or not?
Uh, circuit diagram. Yeah, that's the thing. I think I have the basic, but I dig out some of my old notes. Right? I couldn't really remember much.
It's okay. It's okay. It's the notes probably won't lah. Okay, but
Yeah.
I'm glad you got to this point, right? I'm glad you got to
Yeah.
this point.
Okay.
So I hope you understand that all these are states lah. Huh? Okay.
Yep. Yep. Yes.
How many states are there? 1, 2, 3, 4, 5, 6, 7 states lah. So this one can be encoded as 3 flip-flops. I hope you understand that lah. Huh? Can ah?
Yep. Yeah. Can.
Okay, so I just going to go ahead and draw the 3 flip-flops lah.
Yep.
1, 2, 3 lah. And then for completeness sake lah, it might be nice lah if you just put here. You can, if you want to put a little table here for completeness sake lah.
Okay.
Put a little table here. You can just put lah state lah. Okay, then you put
Okay.
here S0, then just put something lah. I'm not too concerned about this because ultimately the encoding Verilog
Yeah.
can encode it lah. But it's just I want to kind of focus more on the implementation. You see, okay, here is where I'm going to borrow from. From our case study diagram here. Okay, so I'm going to use my multiplexer approach again because it's really one of the best ways I have to explain this lah. Okay, you can follow it, right? The multiplexer approach.
Yeah. Yeah.
Okay.
But yeah, the thing is, yeah, it's still kind of a high level, so I'm not sure how do I transform this into into actual implementation.
Okay, fine, no
Yeah.
problem. We can cover that very briefly. That's going to be very quick to show you actually.
Okay.
Because the key step is first, can you understand the multiplexer implementation lah? That's the key step. Okay, I'm just going to group all these three here, and I'm going to make this very fat lah. So I make this very fat. You understand that this is just this is a bus lah. Okay, there's 3 bits. It's going through 3-bit flip flop lah. Okay, can can It's just an abuse of notation Okay, so basically you're trying to decide how to go to the next state based on the present state lah. So I call the present state, I call it state or I just call this the output here is, let's call it state let's say 2 to 0 these 3 bits, right? Okay, so how many states will I have? Okay, let's look at your state transition diagram
Yeah.
The state transition diagram, we look at your inputs. Okay, the inputs that will transition you will transition on input num, you transition on input num, input timer, input reset lah. So there are 3 conditions that will cause the state transitions, right?
Yeah.
Input num, input 4 input confirm, input reset, input timer. Okay, so these are the 4 conditions that will cause you state transition. So since they're the 4 conditions that will cause you state transition, they go into the conditional side of your multiplexer. Okay, so here I will have a vector. I will have a signal, signal. Let's go. This is a concatenation operator lah from Verilog. You do know that, right? Okay, input timer, input confirm, and the other one what's input?
Yeah, there's also one more is a physical key and error count limit.
Okay, just put all of it there.
Okay.
Input. What's the fourth one? Input.
Input confirm, input timer, input reset, input number.
Input reset, and then physical key, is it?
Yeah, physical key, and there's one more password compare success and error count limit as well.
Okay, physical key.
Yeah.
Okay, this one you're going. Let me check the logic here. You're going here. Okay. Okay, never mind. Just in the spirit lah of this being dumb and easy to do. Physical key and password compare success. Is that all?
Yeah, and one more is a error count limit.
Count limit. Okay. Okay, this is a great example lah. So how many bits we have here? 1, 2, 3, 4, 5, 6, 7 bits. So these options you have to list down 7 bits lah. So I would now encourage you, because this is easy to see as a bitwise, all your conditions to list them out. You basically have to put 7 bits loh. 7B111 000 0. Okay. So you will have 128 conditions here lah. You got that?
Okay.
All right. But some of the conditions you can simplify, because you can actually pretty much put don't cares. Okay.
Yeah.
Why? Because if you look at these transitions, all you don't really care about the key, and you don't really care about this one, right? So all these can be don't cares lah, because the actual transition is only triggered on one. Right, but you have to be very careful lah. Basically, is the idea that input num equals 0, you don't care. Input 1 num also you don't care lah. Right, you're just conditioning on that lah. So that will actually reduce the number of conditions lah. Okay, so I think, is it okay if I say like just based on this, you put in the inputs here, you can put in the next state, no problem, right? Okay, that one no problem, right? Okay, if that one's no problem, now I'll show you how to convert this into circuit. Okay, then we will go on to the process of including the other two state machines. Can or not? So in that sequence, so if you can see already, for example, this where basically this is the state. It's actually fine if you just put this like that. You just list all of them. It's okay lah. It's fine for me lah. So basically, the number of conditions you have to do is you're starting at state 0. So the other thing you have to do is also you have to have a conditioning on the state lah. So this is a conditioning on the input. Okay, there's another one that you have to condition on the state. That is what's your state here before you have that selection lah. So then here is where it's a little bit tricky. You see which one is easier for you to think about lah. For me, it's probably easier for me to think about things in terms of state first lah.
Okay.
That's for me lah, because then I can just say if I'm in state 1, then I just go state 1, then I know state 1 what are the input output transitions. I directly encode for that lah. Okay, so here I will actually put this is your state log, your current state, because it's dependent on your state. You understand me? No, it's dependent on your state. The transition is dependent on two things lah, which is the inputs as well as the current state. The current state is nothing else but the output of here lah. Okay, can or not?
Okay. Yeah, I will follow you first, and then
Okay. Then you ask the questions lah. Okay, so here again you can go back to your encoding lah. But if you don't want to do encoding, also for me, it's also enough you put the state here.
Okay.
Enough for me lah. I will understand this diagram like that. Okay. Because I will show you how to map it to Verilog. Okay. So here you go S00, S01 lah. So S01 lah. So the nice thing about this is now I will show you how to map it lah. So here what's going to happen is you will have pretty much one multiplexer for each state loh. So this is for state 0, 0, you have one multiplexer like that loh. So now you go to state 0, 0, state 0 here. Let's look at all the possible conditions loh. If you're currently in this state, you just look at the arrows lah, the arrows out, the outgoing arrows, not the incoming arrows, right?
Okay.
The outgoing arrows, because you are going to set the next state. So here I only have one outgoing arrow here to state 0, 1, to state 0, 7, and to state 0, 5 lah. I've got only 3 outgoing arrows, and the rest I'm going to go back to state 0, 0 lah. Okay?
Yep. Yeah.
So pretty much I've only got 4 conditions. Only got 4 conditions here lah. Okay, I've only got 4 conditions, right? So I'll go ahead and just put the state first. Then we'll figure out what are the conditions that make you transition lah. Okay, so I'll go ahead and put all the states here first. You can retain in the same state, state 0, state 0. You can go to state 0, state 7, or state 1 lah. This is the next one. 0, 1 first. You can go to state 0, state 7, and then you can go to state 0, state 5 lah. This is clear, right? Right, now let's go to state 0, state 0 first. No, that's the biggest state lah. So let's go to state 0, state 1 first, the one particle. So that only transition when input num is 1. Okay, so let's look at the other ones. Info confirm. So info confirm means I'm assuming the rest are 0 lah, right? Yeah. So here, because you have 7 conditions, you know, okay, 7 input transition conditions. So implicitly you must understand that there are 128 arrows emanating from this, you know.
Okay.
Okay, but we don't draw 128 because we assume don't care for the rest lah. So like input num is 1. This transition means input num is 1. Everything else is a don't care.
Yeah.
That means the other 6 bits are don't care. Input num is 1. Here input confirm is 1. The other 6 bits are don't care. And now here you start to see a problem lah. Does input num take precedence or input confirm take precedence?
Okay.
Right? But like I said, telling you that the theory is to keep yourself sane. You need to ensure that there are 128 arrows coming out of here, corresponding to all possible combination, all possible bit combinations of these input signals that transition. Okay. So here is where the refinement is. You must specify the priority input confirm. Input num don't care or what lah, right? Because this one, if you put input confirm is the priority, input num don't care, that means here is assuming input confirm is 0.
Okay.
Right? So you have to establish that lah. So I'm going to go ahead and do that lah. I'm just going to go ahead and say maybe input reset is the priority lah.
Okay.
My order of priority of the bits, I can actually just say order priority lah. So I hope you understand lah. If this one does not mean the rest are don't care, right? Because there could be a case if here you say don't care, so then you have overlapping situation in these 2 arrows, right? So you must specify an order of priority. If you say this one is 1, everything don't care, that means here input confirm has to be 0, and so on and so forth lah. All right?
Okay.
Can follow
Okay, I have to see the.
Okay. If you cannot follow at the moment, let's just assume we have these 2 arrows at the moment. Let's just assume we have these 3 arrows. Okay, that means I only got 2 bits, right? I got only 2 bits: input num and input confirm. No, okay, input num and input confirm. No, okay. Let's say for now lah, just for the sake of discussion to illustrate the problem to you, I got input num and input confirm only lah. Okay, 2 bits. What are my possible combinations? I can have input num 0, input confirm 0, input like that, 1 0 1 1, right?
Yep.
Right, now you look at these 4 possible combination. You say input num equals 1 here, right?
Yeah.
Input num equals 1 corresponds to these 2 conditions where input 0, input confirm can be 0, input confirm can be 1. Okay. Input confirm 1 corresponds to 2 situations. These 2. So you have a problem because your problem is that when you have this input num equals 1, input 0, input num equals 1 and input confirm is 1, your state is supposed to go here or go here because it meets both conditions. You see or not?
Okay, yeah.
Right. So that's why I said you have to specify the order of priority. Like if you say input confirm has the priority,
Mhm.
you would say something like 1x like that, and you
Okay.
eliminate this lah,
Oh, okay.
right?
Okay.
So this is equivalent to saying, like I said, sorry, this is if input num has a priority lah. Okay, then this is equivalent to saying that your input confirm branch is not
Mm-hmm.
just input confirm 1, it's input num 0 as well.
Now, 0. Okay.
All right, Ken?
Mm.
Right. So I like you to, when you list down all the inputs like that, straight away you know there are 2 to the power of 7 combinations. So that means there are 2 to the power of 7 arrows that have to come out of this block lah. So just now we had 2 inputs, so we have 4 arrows. Look. So
Mm-hmm.
that's why so easily I can tell you 4 arrows, there's some overlapping conditions lah. Okay.
Okay.
So this one you have 2 to the power of 7, you have to be aware of that lah. So it's easy to see if you start putting don't cares like this lah, because then you know everything else you don't care lor, right? Okay, because this one encompasses 1 1 and 1 0 lor. So it's quite easy to see lah. This one is on the case input confirm is the input num has to be 0 lah. Okay, can
Okay.
okay, that's what you have to watch out for. So maybe if you like also lah, but this is harder for me to read lah. I can always put priority encoder list lah, because this is
Okay.
nothing else but a priority encoder. You're encoding priority to input confirm lah. You can put, sorry, input num is the priority lah. You can put input num,
Okay.
input confirm. So if you want, you can actually list it out this way as well lah.
Okay.
But it's better to write something like this, easier to see lah. Okay, but now that we've established that, so maybe we put input for input reset should actually have the priority lah.
Mm-hmm.
Okay, but here you don't actually care, right? Here you only care about input num and input confirm lah. So we maintain this priority. We go ahead and specify lah what are the 4 states. Actually, there are only 3 states loh. Why? Because it's input num. Okay, let's now go back to our this is the priority we're observing, but we go back to our input is 7 bits low. Okay, so here input num, input timer. So input timer you can actually say don't care low. So when you put don't care, all this will reduce to only 4 bits low. So you don't care about everything else except input num and input confirm low. Input confirm is the third one, so you can put you can see essentially this is only set by these 4 values, 0 0, 4 conditions, 0 1
Okay.
0 1 1, correct? You can follow me with that, right? So now we see if both are 0, then of course you stay in state 0.
Okay.
If input confirm is 1,
Mm-hmm.
you go to S5 presumably, right? Input
Yeah, that's
confirm
fine.
is 1, you go to S5, right?
Mm.
So if input confirm is 1, you go to S5. And again, we said, but that's only if input num is 0 lah. Okay, if input num is 0, if input num is 1,
Okay.
this one they're the same lah. So basically these two you can actually do this, and you basically can erase this one lah.
Mm-hmm.
Can you see it?
Okay. Okay.
Okay. And then if you look at this, you can further simplify it lah. You can further simplify it by saying, hey, it's only just based on 2 bits. So I can just basically remove these 2 bits. So this now can become a 2-bit signal, like that. You understand what I'm saying?
Okay. Okay.
Okay, but I prefer you to maintain the 7 bits in the
Yeah.
beginning at least lah, because this is a systematic way. It's a recipe. If you do this way, you're not going to forget about missing bits and all that lah, because you know that this 7 controls everything. So you just go through it. So we figure out for the first case already. Now you can figure out for the second case, which is, let's say you're in state 1.
Mm-hmm.
You go through it. You're in state 1. And Now I look back at my data. Okay, maybe I don't pick state 1. I pick a more interesting. And my state 1 is okay. I can pick state 1 for now. So what are the four? It's still the same thing like input num, input timer, input reset, input confirm lah. So there are only going to be 4 that matter, right? Okay. So they're going to be 4 that matter. So I'm going to have 16 combinations lah, to the power of 4 loh. Well, input num, input timer, input confirm, input reset. And compare success, these 3 don't matter lah. So I'm going to have 16 of these, 16 possible states, right? Because there are 4 bits that don't matter, right? But I can now set the priority loh. Here my priority would be okay, let me close this first lah. My priority would be, okay, maybe I put num, of course input reset should always have the priority, right? And then input timer will be the last priority lah, like that, no? Input timer lah. So I can do this because I've not changed the priority of the previous one, input num and this one lah. Okay, so I can put, let's say if reset is 1, everything is don't care lor. Okay, then if reset is 0, input num is 1, everything is don't care lor. Input confirm that. It should have 16 combinations, right? But now we have 4. This is understandable lah. So there are already 2 combinations here, lor. Okay, so there are 1, 2, 3, 4 here. If you can follow me, there are 4 combinations here, lor, right? Because there's 2 bits here, right? Blank out. There are 4 combinations here, 4 and then 4 here, so there are 8 here, lor. And there are 8 combinations here, so there are 16 in total, lor. But you need to only enumerate 5 lah. Right? 5, so I can have those 4 conditions lah. 1. Okay, so probably it would be good for us to rearrange this to reflect the priority lah. Then it becomes easier to read, you see. Num confirm. So I can put 0, 1, x, input 1, x, and then I can put and then here there's 5 lah. So if you don't want to draw arrows, you can just put this by the side lah.
Okay.
Okay, I think I can understand it lah. Okay. Gabriel, give me a second.
Yeah, sure, no worries.
Oh, very bad, are you?
Okay, Gabriel. Okay,
Yeah.
Back.
No worries.
Okay, so if you're in state 1,
Yeah.
then what happens when you get input reset lah? So you go back to state 0, correct? Okay, you're in state 1. You're in state 1, you get input reset, you go to state 0 lah.
Change really right, heavy really.
Go and change.
Go and change. Heavy or?
Go and change. Go and change. Okay, sorry, Gabriel. So there are 2 transitions back to state 0. Input 1 timer, input 1 reset lah. Okay. Input 1 timer, input 1 timer, input 1 reset lah. Reset is the last one. This one maintains state 1 lah. There's no change. This is state 0. Okay, like that. All right. Then you have to go input num. You go to state 2 loh. This one you go to state 2. And then this one will be input confirm. You go to state 5 lah. Correct.
Okay.
So we're done with this. Okay. Do you follow?
Yeah.
Okay. Ken, sorry, I'm pushing you a little bit faster because if you can get it, we move on. Okay.
Yeah, no. Yep.
So okay, so here quite straightforward lah. I think you get the point. It's just how much more complicated it is lah. So it will get a little bit different on this, but you get the point. I think you can finish up the table lah, right? Because that's a nice thing about you listing out all the input, the bit signals for you to transition. That's a nice thing. Okay, this is just a state machine. We're not talking about how you generate these outputs yet. Okay, right. So based on this, the thing you should understand now is I can write a simple Verilog for this now very easily. That's the nice thing about this. Why?
Okay.
Because basically my flip-flops always at, okay, so I apologize to you, I'm not updated to Verilog, system Verilog lah. I'm just using the old version, but it still works lah. So post H clock lah, begin, and that, okay, this is all right. So I declare reg state, reg. Not going to care about the caps lah. Actually, you're not supposed to have caps.
I can do that. Yeah.
Okay, so right. Okay, so here I'm actually basically I told you that this is always written as this post H clock takes care already. You're talking about the next state, of state. Okay, so I always use a non-blocking assignment. It's easier. For me, it's easier. I don't really like the blocking assignment lah, unless you know what, because that one has order of precedence. This one no order of precedence. Okay, so this one very simple. You're setting the next state depending on two conditions. No? Okay, so basically the simplest is actually to put a case statement here. Okay.
Yeah.
So the simplest is a case statement. You can do a nested case statement. That's fine, right? So the first case statement will be this 7 state. The next will be this lah. Or if you are crazy like me, you basically define assign inputs lah. You can actually assign. You can concatenate all of it lah. Reset. On lah, okay. If you're sort of crazy like me, you can actually just concatenate all of that lah. Your case statement now becomes, okay, for the first case, state 0. So is whatever state 0. So this one would actually be in total 7 plus 3. So it's 10, no? 10 bits, right? And actually the separator doesn't matter, no? So you can put the first 7, no? 0, x, 0, x, 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 x. Then the 3 bits for the state, lo, which I will just call SSS. La. Okay. This is a 3 bit for that. That's why the encoding is here. Lo. Right. Like that. Lo. Then you can put like that. The state. So this one you are encoding this branch as 0, 0 lah. Okay. So this is one way to do it. This is if you just want to have one level of case lah. If you want to have 2 level of case, also can. That will be a bit simpler lah, because then you can actually just put the state name here. Then up here you actually have your parameter. The S0 equals 3 bit, like that. That's fine already. Then what this would do is you will just replace this with this. Then you can actually put the second level case statement here. This one will be easier to see lah. Okay, so the case statement here will be based on the 7 values lah, inputs lah. Okay, I can put here 7 B0 X0 XXXX. So here I can just directly list all the conditions. No? So here this is state 0 ma, so I can just list the second condition, just read it out. 0x1 xxxx, then state is goes to S0 to S5. Then here 7b1 xx xxxx state. Really easy to do. I'm done here for state 0. Then I do state 1. State 1. Another case statement here. Case statement here on inputs again. Okay. Follow me, Gabriel?
Yeah.
You see, it's really easy, right? So once you list it out, it's just really easy. I'm just looking at my diagram and copying everything out only.
Okay. Okay.
You see or not? You see why this is easy, right? So if you want to have it simpler, of course you can concatenate lah. You can concatenate two states so you don't have the nested state lah. But in this is an implementation where I don't concatenate lah. I don't concatenate so that you can actually see it lah. But if I were to write it, I would concatenate lah because actually it's just a single 10-bit marks also can already, right? It's just you're setting the bits, you know, right? You can actually condition only on the 10-bit, which is state on the first 3 bits followed by the rest.
Okay.
Ken, I'm pushing you here a little bit. I'm recording this session, but later you can reference lah.
Yeah.
If you cannot, never mind. You do this first session. There's no harm. The optimizer will take care of it. No problem.
Okay.
Okay. So you see, this is really easy. It's really straightforward, and the best part is I know I covered every situation because I'm literally going along the line of every arrow I've accounted for in the number of inputs and all that. So I know I'm fine. I know I've not missed any cases in this case, right? Because of the methodology we've gone through just now, the way I asked you to make sure you've got 7 bits, you account for every possibility, you make sure the priority encoding is set and all that. Okay?
Okay.
That part is okay. Yeah? So from here, I hope you accept that this one can be converted into digital circuit. Okay? Okay. That is the easy way out lah. The difficult way out is, of course, now you can, of course, always draw a truth table for this if you are looking for pain and suffering. You're welcome to do that once in your life just to convince yourself it works. No, it's good. You just have to convince yourself it works lah. So what is my truth table here? Okay, so you're actually basically you're trying to actually specify these output bits as a function of how many bits? 3 state bits, 2 bits, right? So you have a 5 input truth table. Okay, right? So you are specifying 5 inputs, 5-bit inputs, and then the output is 5-bit outputs lah. Sorry, 3-bit output lah because you're specifying states, right? Specifying states. So your 5-bit inputs here are basically, I'm looking for the state 0. I'm talking about this one first. Okay, then we do this one. So this one here, you're looking 5 bits. You're looking at, you're basically looking at input num, then input confirm. Then you're looking at state lo, the 3-bit state 2, state 1, state 0 lo. Okay, and you're looking at the 3 outputs lo. So basically this can be very elegantly specified as 0, 0, and then this is state 0, 0 lah. So this is 0, 0, 0. Then you have 0, 1 like that. Then you have 1x like that. And don't care for every other state that is not 0, 0, 0. So you're going to be 0xx and below xx 1xx. Sorry, it's not 0xx. X1, so this everything with 1, and then 0 will be 1. Okay, this is a little bit hard to encode. State 0, 0, 0. I want to have, so you have 1xx, that's correct. Then I have 0, I have 1x, and then I have one more is. So this one all will go to state 0, 0 because they are don't cares, right? And then this one here will go to state 0, 0 because it's the first branch. This one, the second branch here, will go to state 0, 5. This one here will go to state 0, 7. Okay. You can now go to your encoding table, you fill all these things, and then you have fun doing a 5 input K-map with a 3 output. That's fine, no problem. You got it?
Okay.
That is only for this part here, for state 0. Okay, for state 0. So I have a separate K-map for that state 0 lah. Right? Why would I be doing that? Okay, so you can have that separate. So one way to do it would be I can actually do one K-map here, and then I one K-map for this state lah. So maybe what I can do is I can, because this one won't cut it lah. This one you have to use all the state lah. Sorry, So I'm going to remove this. I'm going to just do 2 level lah. So you have one combinational logic that is on here and another combinational logic that is here lah. Okay, so this second combinational logic basically is implementing a multiplexer lah, based on the state. So you're taking the state and then your output 3 output is basically coming from, so state 0, so this output is coming from circuit 1. And circuit 3. So you have one truth table here. These outputs, I call them circuit 1. Then you will just connect when it's state 0, 0, you just connect the output to circuit 1. And then state 0, 1, connect output circuit 2, state 1, 0, circuit 3, state 1, 1, circuit 4, and so on. These are just 3 bits. So this will actually just synthesize into a 8-way multiplexer. That's it. Okay, so the only situation here you have to team is you haven't figured out state 7. State 0 to state 7. You got perfect 8 states, so no problem. Okay, can see how this converts to circuit, right?
Okay.
Okay, yeah, because I'm just using a multiplexer here lah. But again, you got permutations lah. If you want to just combine these two, and then you can reduce the number of bits here. There are many ways to implement this lah. But just trying to say that part not important lah, because once you got this guy already, in fact, you got this guy already, it's already enough. This guy is already a circuit already, right? And then you got this guy already. This guy can synthesize a circuit. But if you want to go all the way, that's how to do it. Okay, that's to tie up your K maps lah. All right. Because the K-maps, when you draw for the flip-flops and all that, the state machine, actually what you're designing the SQ, the Q plus and the Q. Actually, Q plus is just the previous state. Oh, Q is just this low. You're just taking the Q, sorry, Q plus is this input low. Q is just this output low. So you're still designing a combinational logic, but now this is considered the input. That's what you're doing when you design the sequential state machine from your digital logic. If you go and look at it, you're still only designing the truth table for the combinational part, not for the sequential part. Okay?
Okay.
All right. Okay, great. You want a short break or can I push on?
Yeah, you can push on. Yeah.
Can push on, okay. Right, so now I've shown you how to design one of these state machines. Let's look at the output. So the output is very similar because output is state dependent, right? So basically the output is state dependent. So I can actually say the output is state dependent. The state here now will go inside here. And then I have my state here. Okay. So again, what does that matter? Because you specify your output. There are 2 outputs, right? Your outputs are defined not on the transition, but on the state, correct?
Yeah.
All right. So I've got 2 outputs here. My output here will be a 2-bit low. What do I call it? What do you call it? PW match success.
Yeah.
The other one?
The other one is, let me check. Error count limit.
Oh.
No.
Oh.
The output is password condition match, and one more is password error limit.
Okay, password condition match. The other one, password?
Password error limit.
Error limit. Okay. Right. So here again, same recipe. My 8 states look. 8 states look. State 1, state 2, and so on. And here is kind of nice because I can pretty much just read out my 2-bit function. So this is state 1. My 2-bit function is 00, 00, 00, 00, 00, 00, 00, 00, 10, and 01. Okay. So basically you have a whole bunch of, sorry, if you don't need to use arrows, you can just go like that. A whole bunch of taken. State 5. And then there's going to be a state 7, right? You can see how it works, right? So this circuit encodes this complete state transition diagram. So this is your hardware model, right? Because this is directly telling us how to implement the hardware, and I just demonstrated to you. I just read directly from there. I close my eyes. I don't understand what this is doing. Also, I can generate this circuit. That's why it's called a hardware model. Okay, because that is already an implementation. This is an implementation, but it's a higher level abstraction. Okay. So based on this, same argument, you can write the case statement for this. So there are two ways to do it lah. But one would actually be to do what we call sensitivity list lah. I don't like this way. I don't like this way, but it's a bit more competent. I like the other way. This way is basically you have to look at all the possible inputs. Okay, so state is the only possible input lah. So whenever any bit of state change, the output will change. Right, but the problem is if you miss at least even one, you will synthesize a latch, and then you have weird bugs. I don't like to do it this way lah. So if you do always statement, you can of course also just have this as a case statement lah. Okay, you can have this as a depending on state. Then your output will be register. It's basically you can just say lah KW condition. Kind of thing lah. So the state, depending on the state, you can do state 0, state 0, state 0. You can still do, let's say, like that lah. It's not a problem. This is permitted by Verilog syntax and so on lah. In the end case, I don't like this way of doing things. I really don't. Why? Because it's confusing and I may have make mistake if I miss even one bit. I prefer actually all my combinational circuits. I prefer to use assign statements.
Okay.
So assign statement, I can just do a assign like that. Okay, and then I use this operator. 1 0 lah. And the way I do this is you can actually just do lah state if state equals S0 S0, okay lah. Because this one here has to be a bit operation, 1 or 0. So if it's true, I set it to 2B00 lo. If it's false, I have another conditional one lo. If it's false, I bleed through lo. I have a conditional one here lo. Another conditional one here lo. If it's false, I check whether state equals state 1 lah.
Okay.
And then if it's true, I set it to be 2B00 lo. And so on lah. But here actually I have some interesting thing. Everything else is 2B00 except only these two conditions. So I can be a little bit smart and I said state 7, state 5, and then the else condition is actually just don't need to check the state, you just set it to 2B00, you see?
Yep.
The false condition would be here, true, then the false condition else is, sorry, this will be state 7 will be 0, 1. This one will be 1, 0, then this one will be 2B00. So everything else will fall into that. Okay. So you're only checking for state 7, state 5, then everything else will be the false condition. Okay. And if you're even smarter, you will know that the bit is actually dependent on state. This is whether it's state 5 and state 7 lah. So you can actually even do something even more crazy lah. So you just go for bitwise operator. If state equals state S0 state 7. Okay. Sorry, you can even do this. So you're doing bitwise, you know. So if it's 1, otherwise you set it to 0 lo. And then here you do that. So this will sort of give you different implementations, but you get the point lah. Sorry, this is going to be state 7, but this is going to be state 5. Okay, so many ways to do this, but I just show you the easiest way lah from there lah. Okay, but if it's very long, you can always use an always statement and do the case statement lah. If it's very long lah. Okay, or you can do nested kind of if else lah. This is an if else statement. Okay, but it's assigned. But I like it this way because I really I basically can get into the mode that combinational logic, there's no flip flop, is all assigned. Anything with flip flop is here. Okay.
Okay.
There's another way people do it as well. Sometimes they separate out. There's another way they do it as well. I just share with you different coding styles. This is also another way to do it. Pause age clock, where you are still conditioning on the state, but this one is state transition. This one is output. So this one also is okay. This one is state transition. This one is only for output. So you can actually just have outputs. This is also another way to do it.
Okay.
But I recommend you to split them up so that you know this is the control path, this is the data path lah. And this one you have to be a bit careful because this one will update only at the clock age lah. So if you expect this one to sort of change, let's say if there's no clock here, let's say if a gated clock here, this is not changing, this will forever never change. You have to be very aware of that. That's why different coding styles, you have to be aware lah. So this one is sort of safe lah because it's combinational logic. It's based on the state input and all that. So if the state doesn't change, this one doesn't change lah. But if there's any other inputs, right? Let's say this one is just dependent on an input signal. This is actually dependent on some kind of input signal lah. Let's say this is dependent on, let's say PW input num or something like that, right? Okay. So if you use this coding style, even if there's no clock, if this clock is frozen or not moving, or the clock is not moving, this output will still change lah based on input num because it's coded as an assigned statement. But this one, the output totally won't change lah, right? Because this one, the way you encode it is somehow the input num will go through a flip flop or something like that lah. So if there's no clock, there's no output already.
Okay.
Okay, so you just have to be very careful what state encoding you're using. So if you're using a Moore machine, meaning that the output is actually tied to the state, no problem. You can always use this with a Moore machine because there's not going to be an input like that. With this kind of input, this is a milli machine encoding. With this kind of input here, this is milli machine. This means corresponds to your output will be here, your output will be over here. Is depending on the transition, depending on this particular input, this transition. That means it will also be depend on input confirm lah. Okay.
Okay.
Okay. So right now you're coded it as Moore machine. This is no problem. You can go ahead and use this. It's probably going to be simpler also lah to code out. But just remember, if you actually happen to encode milli machine, which means your output is not here, your output is dependent on the transition here. You have to take into account this particular transition. That will be those inputs that are also combining with the state to give you the output. And then it's not safe to use this coding.
Okay.
All right. All right, great. So now you, very crash course, you know how to encode one state machine lah.
Yeah.
Okay, you can go ahead and design this lah, and you can go ahead and design this. And the only difference is here, this is an output. The output will be one of the inputs to this state machine.
Yeah, okay.
They're pretty decoupled actually. That's the nice thing about this. It allows you to reason about it lah. So this is running. You can go ahead and design this, and then just the output there is the input to here lah. So you just have to make sure you have no kind of crazy circular logic lah.
Okay.
Because again here, the inputs here can also be an input state here, you see. But as long as you ensure that whatever is coming from here is always well defined, and whatever is going from here is always well defined, you should have no problem. You can have cross-coupling state machines.
Okay.
Right?
Okay.
So you go ahead and try it out. Just encode all these right in Verilog and simulate it, and you will see very nicely that it will function. It should function. If you don't, just WhatsApp me and then we'll have a look at it.
Okay. So like
Okay.
yeah. In
Yeah, sorry, go
hindsight, my hardware transition diagram is okay, right? If let's say you can see this system, and when I draw the inputs and as well as this system, then it matches okay, right?
Okay, the way I would say it here I'm a bit lost here lah. Because
Okay.
what I can see is you have PW combination match from here.
Yep.
And your PW error limit is from here lah. So
Yep.
that influences these two branches and maybe this one. But I don't get your door timer and your door sensor lah. What happens lah? Because if the door opens too long,
Yeah.
then you're going back to this state, but the door is open, no? Like, do you shut it?
Yeah, so we have to shut it. So when the door sensor detects that the door is
This
closed.
one is okay. So this
Yeah.
is why you have to actually put down the label lah. Door sensor
Okay.
is one. Okay. So the other thing here is that there's a problem. The
Okay.
problem is when your door is open, this thing is still running, you know. So I can
Oh.
still put in the right and then it can actually lock. So there's a problem, you know, right? Because this thing can suddenly match or it can suddenly not match and then you latch things. So what's happening lah? So if it matches or don't match, then okay lah, I guess you have this state sort of defined, but you just have to double check. Do you want that or do you want some kind of signal to come back here that when you're in these two door open states, you actually pretty much force it back to state zero lah. You
Okay.
see, not? So the difference is just in functionality. The way you're doing this now, I give you an example. Like you do it is the door is open. Of course, whatever happens here is not going to influence here, but the state is still running. You can put 3 buttons and then it's like hanging somewhere here, right? So if you close the door at this state,
Mhm.
where are you going? You know, if if you close the door at this state, these things are 0, but it may actually be at state 3 here. So you enter another 2 more and then you'll be in error button lah. It's not too bad. It will still work because this one you actually have logic that will actually go back to the waiting state lah. No problem lah. So it's fine actually. It's just the functionality that you will design lah. It's just that, you know, when this is in these two states, you sort of just probably ignore anything that's happening here. That means if the door is open, you can go ahead and reset the password and all that kind of things lah. So you can go ahead and do that kind of things even when the door is open or when the door is closed or when it's actually in the wrong pass. You can go ahead and do that lah. It looks to me like that lah. So if you really want to tighten this up, which is not a necessity, it's just like I say, it's functionality, it's up to you. You can actually have a signal coming out that if sensor equals 1, you force
Oh. Okay.
any state to come back lah, because when sensor equals 1, when sensor equals 0 lah, this is open, right? Right, because you only look at the door sensor when you're in the open state, right?
Yeah.
So sensor 1 means is closed lah.
Close. Yep.
So the door sensor 1 is closed lah. Sensor. So here condition met. Okay, so sensor equals 0. So you have a door sensor lah. Okay. Door sensor equals to 1, you always go back lah. Okay, yeah, so that's fine. It's quite foolproof. So you can actually have maybe a door sensor. Once a door sensor is equals to 0, you can actually just force it to stick into one state lah. No problem lah. But you have an 8-bit lah. But even if you leave it like these two, at this moment, I can't see any catastrophic failure, so it will still pass. Okay, Gabriel?
Okay. Okay.
All right. Okay, so these are considered nested lah, but you're missing the timer function. So you presumably will have one more state transition diagram just for the input timer lah. Okay.
Okay.
Right, that's missing. And then one more thing is missing is your password lo. So like I said, here you actually have a comparison operation. So again here, what is missing? Okay, good. What is missing is you've not defined the logic to generate all of these input signals. You have 7, probably 8 input signals here. You've designed the control path, you've designed the data path, great, but it's not finished because you haven't defined the logic for all these control signals. Okay. So the logic for these control signals can come from another state machine, as is the case of input timer. They can come from a simple input, in the case of input reset is a button, okay? Or it can come from some kind of logical operation, which is PW compare success, okay? But you have to define PW compare success. You've got the 5 inputs buttons here, but in this circuit, I don't see where you're storing the actual button, okay? So that's
Yeah, so my idea was like you press a key, right, and then you actually detect you press the key. So that's the reasoning behind input num.
No, that's fine. I'm not criticizing this, you know.
Yeah.
Okay,
Okay.
it's possible, right? It's possible you press any key. So any
Yep.
key press, there's just a signal coming up to do the transition.
Yeah.
That's input num. No problem. But what I'm saying is that in this particular circuit or implementation, it is not defined where you are storing, right? Because this kind of
Yeah.
architecture, it looks like me, you're setting up yourself for shift register. So you have the input num going here, but the number of the key is actually going to go into a shift register. So there's going to be a parallel flip-flop path chain here. The key number is going to go in, and then the next clock is the next input num is going to propagate down the shift register. So at the end of 5 button presses, you've got the 5 numbers in the shift register. You can actually use the shift register to do an equalizer to compare with the actual password lah. So you basically will have 2 shift registers. One that will receive the inputs from and it's actually clocked on input num, okay, that shift registered. The second will be a shift register storing your password. So when you go into this branch, you're updating the second shift register. You go into this branch, you're updating the first shift register. You see where I'm going with that?
Yep. Yep.
That's one way to implement it. Another way would be you just do memory. So you have this one 0, 0, 1, 0, 2. So when you actually transition here, you're actually writing into the memory at this particular address location that is given by the state output. That is if you want to use the state output. So another way is you can actually just store it in RAM. No problem. Okay.
Okay.
Because what I'm saying now is that it's not completely circuit because you haven't shown how your numbers are stored and you also haven't defined all this logic, but the major one is the PW compare success you haven't defined. The 5 key I presume is coming from a sensor so never mind Then the error count limit also you haven't defined, right? Because there's going to be arbitrary number of errors I see, right? From here you're going to actually go to here and then kind of keep counting or something like that. You go here, I think, okay, there's a problem here. You have an error count limit. How many counts you're limiting? Up to 5?
Yeah, up to 5. Yeah.
So after 5, you're just going to straight away jump to error
Yeah.
Okay, fine. So you have the error count limit, you hit here, and then it will just keep going on until you reset it with the key So once you got, let's say if someone puts in 6 keys, you're going to force the system to totally shut down until you have a key, is it?
Yeah, so if they entered more than that, definitely they will increase the error count limit.
Okay, so here there's probably a point of confusion Maybe what you're thinking about is number of tries Like say I put a 5 key password wrong, then I put it again wrong, then I put it again. The third time you want to freeze it right? Because that's not reflected here. The error key limit here, you're just saying after I put in the 5th one, if I put in a 6th button, straight away I'll freeze it. So you're not actually capturing in here the repeated 3 times to lock it Okay, so if you wanted to have actually 3 times of 5 keys, right, you can wrong. So basically the way to do it is you have another state machine that's actually just doing a counter, right? So whenever there is a failure, the failure will increment the counter 1. There's another failure, you implement the counter 2. Then the third failure, you implement the counter 3. When there's a counter 3, there's another signal here. Instead of allowing yourself to go through here, you just jump straight into this state. You see or not?
Yeah, so I think there's one arrow on the left. It says if it doesn't compare success, right? And then you go back to the initial state and then you try again.
Which one?
Yeah, password compare
success.
Yeah.
No, this one says it's not successful, right? Because
Yeah,
you
it's not successful.
input your 5 keys here. This one, if it's not successful, this one, if it's successful. But in these both branches, you are doing one comparison.
Yep.
Okay. But what I'm talking about is after you do one round of this, not successful. The second round of this, not successful. The third round of this, not successful. You probably want to lock it.
Oh,
So
so
here, what it looks like for me is you do 5 buttons, and then I don't know where error count limit is incremented
okay.
Right, so there needs to be another counter and that counter, another state machine will get triggered on whenever there's a PR compare success 0, whenever there's a transition from here to here right? Because the PR compare success 0 is the default, right? Even in all these states, this is going to be 0, right? So whenever you make the transition from here to here, you have to set some kind of signal 1 true right? So you have to set that signal lah, right? And that signal has to trigger a counter, and then once that counter counts to error count limit, then only you generate a signal. So I think it's still consistent. What we're saying is that you have not figured out how to implement all these control signals lah.
Yeah. Okay.
Right. So once you figure out, we can discuss again. No problem.
Okay. Sure. Then yeah, let me digest everything first.
Okay, Ken. I'll just share this with you. Are you okay if I share this recording with the other colleagues, the friends?
Yeah. Sure. No worries.
Okay. I wait a bit lah. Let them do a bit of work first lah. Okay. All right.
Yeah.
Okay. So after this, I'll share this with you. You are accepting this through UTP account, right?
UTP account. Yeah. The Microsoft Teams, right?
Okay.
Yep.
So if UTP account, you can directly access the recording already lah. All right. Okay. Right. But never mind lah. I'll just also upload it.